Hello, everyone, and welcome to the Fault2SHA Learning Series. I'm delighted today to invite Yehuda Bock, who will be talking to us about measuring fault displacements using GNSS. Yehuda is a distinguished researcher and director at the Scripps Orbit and Permanent Array Center at UC San Diego. I'm sure most of you have already heard of him. To put his achievements in some form of perspective, he has over 17,500 citations for his work and an H-index of 69 when I last checked, which means he has 69 papers which have been cited at least 69 times. So we are in very good hands today, and I'm absolutely delighted that he could join us. As I mentioned before in previous sessions, this is our 6th learning series. The point of this series really is to help all of us working in fault-based seismic hazard assessment to learn about different disciplines related to this and to help us understand the fundamentals. Often we go to seminars and to research conferences where maybe somebody has 10 or 12 minutes to describe their latest research, not allowing that time to provide the introduction. So the idea behind this learning series is to give us a chance to learn a bit more about the basics, about the fundamentals, learn from those who really know what they're talking about to help us collaborate across different disciplines and hopefully promote better use of faults in seismic hazard assessments in the future. So with that, I will hand over to Yehuda. As always, if you have any questions as you go along, if you want more explanation, please do interrupt. Yehuda's happy for people to interrupt and ask questions, and there'll also be some time at the end. But the important thing is that we all understand as we go along. So thank you again, Yehuda, and over to you.
Hello, everybody. Thanks, Joanna, for the invitation. I'm really happy to join in with you today and contribute to your learning series. So today I'm going to talk about measuring fault displacements using GNSS, or this Global Navigation Satellite Systems. And I am located in San Diego right now. And on the bottom, I have some of the people who've contributed to parts of this presentation, and students, postdocs, and other researchers. Okay, now there's a wide variety of different hazards that can be studied with geodetic methods. And I just listed some of them here: the earthquakes and tsunamis, volcanoes, landslides, flooding, extreme weather events, and things along those lines. And today I'm going to focus on the earthquakes with some discussion about tsunami warnings. So summarizing, we're talking about risk here, about that hazard, excuse me, as part of risk and mitigating of hazards. And so that's our focus. I'm going to summarize. We have talking about geodetic methods, then GNSS time series displacements, the crustal deformation cycle, focus a bit on transient deformation that complicates hazards assessment, fault slip models, post-seismic deformation, and then local tsunami early warning. Okay, as far as earthquake hazards, the basic information that we want to achieve are mapping of geologic faults, their geometries, and their slip rates. How much are they moving within the crust? How much energy is released in a certain amount of time, or with the magnitude that you can expect? What are the probabilities and the frequencies of occurrence? And from that, derive what are the expected ground motions. So I'm going to be discussing the mapping of the faults of geometries and slip rates, and show how we use GNSS in order to study, to determine these different processes and convert that into hazard assessment. So the GNSS satellite systems, I list them here on the, you see my cursor? Okay, excuse me. So I've worked most of my career with the Global Positioning System, a US-based system that's ubiquitous today. But as most of you are aware, there's other systems today, the GLONA Russian system, the European system, the Chinese system, etc. And so rather than having just one constellation of 24 GPS satellites, we now have about 160 satellites that will be available, which includes about 400 different types of signals, of different frequency signals that are used in order to receive the information from the satellites and then compute from those observations the positions of points on the Earth's surface. Here's a global distribution of GNSS stations. And these are stations that are built specifically for crustal deformation monitoring or for other studying other processes that require precise positioning. So we have thousands of stations you see with the white triangles. And these are all the earthquakes in the brown squares around the Pacific Rim. These are all the earthquakes since 1990, and you see the plate boundaries, various plate boundaries. And we centered the map on the Pacific Rim, which along with the Indonesian archipelago contains the world's major subduction zones and has produced 9 of the largest 10 earthquakes in recorded history. Now, I'm going to be focused more on the Western US. That's primarily where I work, although I have been involved with projects around the world. Okay, so this is a typical, there's 2 types of GNSS. There's a continuous GNSS, where I showed you the thousands of stations around the world. This is a typical station. This is on a hilltop near San Diego, where I am. And typically you'll have this is a receiver. The GPS receiver will be in some kind of enclosure. We have solar panels, radio antennas to transmit the data. We'll also have MET sensors to do called GPS meteorology. And then the antenna is connected through cables to the receiver. There's a covering of the antenna. Most of the stations in the Western US have deeply anchored monuments, we call, and they consist of 4 stainless steel rods. One of them is vertical, and these rods go 10 meters into the ground. So they're they're anchored to the ground, so that we're measuring actual motions that we're interested, rather than some kind of local motion that would be due if a station was on a building, or if you had on a landslide, or you want to make sure that you're tightly coupled with the subsurface, so you're not measuring things that are not related to what you want to measure. Now, there's also what's called a survey mode, GNSS, where people go out and with receivers, and then they'll survey monuments that are on the ground and observe for maybe a few hours or less. This is one of our colleagues, Professor Sanwell, who's doing a GPS survey with a monument that we have to dig out of the ground. But that's a historical picture. So those are the 2 types of deployments that we do: the continuous ones and the survey mode observations. I should say there's another method, which I won't really discuss much today, but it's the Interferometric Synthetic Aperture Radar, or INSAR. And that allows you to, using satellites that are radar satellites that continuously pass over areas on the surface. And by looking at comparing images from one time to another, you can then determine motion on the surface. Now here's an old slide from 1992 Landers earthquake that shows you the an overlay of the. This was the first time that INSAR was used to measure an earthquake, and at that time we only had a few of these GPS receivers. You see them here at the time, and so it kind of shows you the synergy between them is that the GPS will provide you high temporal resolution, and the INSAR will provide you with high spatial resolution. So a lot of our research these days is combining the two types of measurements into a single measurement system, and we've made a lot of progress in that area. I'm going to focus in to the western US. You see here the significant earthquakes since 1992. So we've had quite a bit of opportunities to capture earthquakes. The first one was I showed you in the Landers in 1992, which occurred about a year after we put stations into the ground. And the latest earthquakes that we've had with 2019 called the Crest earthquakes, which has generated a lot of studies. And on the right, you see the continuous GNSS network that we have now in this area. Now, there's about 1,200 or so stations, a little bit more. Those are operating continuously. And most of these now are providing data in real time at a very high sample rate, like once per second, even greater. So I will discuss earlier in the talk, I'm going to be talking about these solutions that we estimate once a day based on 24 hours of data. And then later I'll show some results with these high rate data, which are collected, as I say, once per second. All right, now to first order, we measure, historically, this is what we were looking for, was to measure the interseismic velocities due to tectonic motion. That is, how do the sites, these stations, move over time, mostly in their steady state or just a linear rate. And in this slide on the left, you see the velocities. These are the steady state velocities of the Western US, and you have the transition from the North American plate to the Pacific plate. Here the stations are, and this is actually an international terrestrial reference frame, and the stations on North America are basically moving very little. And as you go across the plate boundary, the velocities will increase to about 50 millimeters a year compared to the fixed North America. And it's a challenge to basically determine the slip rates of how the faults are moving, because there's a large fault system, the San Andreas Fault system, which actually consists of many faults across the plate boundary, which is about a few hundred kilometers wide. So the original goal of the continuous GPS or GNSS was to determine these steady state velocities. When we started, we had very little knowledge about this except from plate motion models. So over the years, we've accumulated more and more information on interseismic velocities. This is a typical displacement time series from this is a station near the Crest earthquake, which has been operating, close to 20 years. And this is, and what this shows here is that we don't only have the steady state linear motion, but we also have transient motions, and you add those together, and that's what you observe. So you don't only observe these steady state, but these transients are things that are of interest, but also can complicate your analysis of the physical process that you're actually looking at. And this is I don't know, people don't appreciate that this is kind of a very intensive process to be able to then take these time series and squeeze out the information that you want with the high accuracy as you can. And so there's a whole bunch of problems that you have to go through in order to really well use these time series. And there are outliers, there are problematic stations, which I'll show you an example. We have to correct for metadata errors, such as if people don't record well what's different antennas or antenna heights that are at the station, that it complicates and introduces spurious artifacts in the time series. If we're looking for tectonic, we also need to look for non-tectonic offsets. Is sometimes you'll change an antenna at the station or a GPS, a different type of antenna, and then you'll get an offset in your time series. You also then have to know where all the earthquakes occur. And so once we go through this process and fix all these problems, then we assume that the motions represent these purely physical processes that we're interested in, such as crustal deformation, cycle, earthquakes, volcanism, hydrology, things like that. All right, so in this slide, you see there's two spurious offsets due to antenna changes. You can't see that because we have it trended and they've been fixed already. We have two earthquakes, the 2010 earthquake, which at this scale doesn't really show an offset, but you have this large offset here during the Ridge Crest earthquakes in 2019. This station is very close to the epicenter of that quake. When you detrend the time series, and you can see, basically you take out this linear rate, and you can see much better the transient motions. Again, you have so you have a linear rate coming into the earthquake, and then you have large co-seismic offset, and then the period of post-seismic motion, where the Earth is relaxing and supposedly going back to its interseismic rate. Eventually, this can take tens of years until it goes back to its steady state velocity. This is in the north component, and this is in the vertical direction. So you see the offset here. There's a vertical offset as well for this particular event. Now the precision here is for a single, each of these makes up 24 hours of data. So for a single position over 24 hours, and you get an RMS about 1 millimeter, 1 to 1.5 millimeters in the horizontal, which meaning that an individual day will have a precision of 1 to 1.5 millimeters. Of course, they're scattered, but this is the root mean square error. The vertical is usually 3 or 4 times greater than that. Right? This is for a single 24-hour measurement. As I mentioned, there are some worst-case scenarios with these time series, which you have to avoid. And this particular case is also a station which is in the Los Angeles area, and it's over time it's been covered by vegetation, which the operators didn't really pay attention to. And so over time, you had obstruction of the antenna. You can barely see the antenna. So you see this spurious deformation, which is only due to the tree being there, this large bush. And once they realized, they cleared the area, and it kind of started going back to its normal behavior. So that's kind of things that you have to be careful about when you put in a station. You really have to keep an eye on it. And one of the hints then is, of course, when you start seeing these time series misbehaving, then you think that something is not exactly right. So this is a really extreme event, but in other types of problem stations, it may not be so apparent, and then you might have it mix up with what you want to measure, which is what we're talking about today, is crustal deformation. Okay, so this is a daily record of surface displacements, and there's a whole list of physical processes that occur especially in a California environment. And on the top, you'll see the earthquake deformation, which you have then the co-seismic and the post-seismic motion, which I talked about already. Then we have areas of volcanic inflation and deflation. We have what's called a Long Valley caldera in Central California, which is uplifting. And that causes also horizontal motions away from the uplift. So we have that kind of deformation, and we also have deformation that's due to water storage on the upper crust level that we have that due primarily to groundwater pumping. So you get these signals that are due to hydrology, and also basically water policy is how much are they pumping, how much are they replenishing the aquifers. Right now we're in a serious drought, and so there's more ground pumping. So we get these signals that are primarily cause subsidence and uplift, but they also are reflected somewhat in the horizontal direction. So you get this kind of signal, which is not a tectonic signal, it's just due to hydrology. So the challenge is to separate these different processes. Okay, I'm here. Let me put it. Haven't been put it into. Let me put it into now PowerPoint mode. So this is a movie of only the transient deformation. So what we've done is we've taken out the motion, the expected motion from an interseismic model that's been published. And so this is the difference after you take out the interseismic motion. These residuals are what's left. And so you see these different vectors. This is in time here. We're going through about a 10-year period, and you have all these different effects. You have this is an accumulation of transient motions over time. So it's starting again. This is the 2010 earthquake. This is post-seismic deformation that's occurring. You have this caldera, Long Valley caldera, which is uplifting, and so you have these horizontal vectors outside of the because of the uplift of this dome. There's other earthquakes that are occurring. We have two tectonic regimes here in California, mostly strike-slip regime in the San Andreas Fault, and then we go further north, we're already in the Cascadia subduction zone. So these are different. This is a kind of all the residual displacements that we see that are relative to a steady state model. So this obviously complicates determining what the long-term rate is over the California, because occasionally you'll have these earthquakes that will then cause these transient motions. And these are the total motions that you saw in the movie. So this is from the period of 2010 through to this 2019 Crest earthquake. And these are only transients. This has nothing to do with the long-term motion. Here's we take these motions and we grid them in the north and east components. And this is how they change over time. So we have these grids for each epoch, each week. And you see how the displacements are accumulating over time. This includes both the steady state velocities plus the transients. For example, you see here, this is the transient from the Ridge Crest earthquake. So that's this feature here is essentially post-seismic deformation. Here you see it in the east component, here you see it in the north component. And so we really have to look at the whole picture of deformation, including the transient motions. Okay, we go a little bit further and then we look at what's called strain rates to see how these are independent of reference frame, and they basically tell you how this basically shows you how the ground is moving, how it's shearing. So it basically will show you in a strike slip fault environment how things are moving with respect to each other. And then the dilatation rate, you see contraction and extension. And this gives us some additional information. I think you've had Ross Stein, who talks about Coulomb stress changes. So this would you see during here's the earthquake. So you have a large increase in strain for this particular earthquake. So it's the strain rate is a really nice way of seeing how the stress in the ground is accumulating as part of the earthquake cycle. Okay, we also look at the vertical motions, and those are due, as I mentioned, to water storage. Also, tectonic motions will cause some vertical uplift and volcano processes. Here we have subsidence in the California Central Valley and the Sacramento valleys, and those are very large displacements on order of meters. This was saturated, but you also see uplift of mountains. There are some complexities down here that are tectonic in nature. And so you do see some crustal deformation is visible in the vertical direction. Very difficult to distinguish tectonic motion from subsidence in these type of areas. That's a challenge. Okay. All right, so how do we use this information for fault slip modeling? So as I mentioned, there's this, and now I'm talking here about the interseismic motion. And we have two types of tectonic environments in California. As I mentioned, we have in the Pacific Northwest, we have thrust earthquakes, subduction zone earthquakes, such as in the Pacific Northwest, Japan, Chile, Indonesia, New Zealand. And there the crust is moving, one plate is moving beneath the other. We have then the GNSS stations on the land areas. Usually you only have land on one side of this trench, although there are places such as Sumatra where you'll have islands. And so we model, then we make some assumptions about the crust. It may have an elastic layer overlying a viscoelastic layer. We have to make a lot of different assumptions. But basically by looking at the movement of the stations on the surface and making assumptions about the rheology of the crust, and knowledge of where the faults are and how they're moving, then we can get a model of how the fault is slipping. At what rate is it moving? And here I'm showing a more strike slip environment, and this is from above. So if you're looking down at the fault, you say you have a fault here, you have GPS, GNSS. I'm always using GPS. That's historically, that's what I've been using. You have a lot of these GNSS stations on the surface. You have there are certain faults that are locked versus creeping. This is important. The locked faults are faults that are basically locked, that are not moving at the fault interface. So they're locked in time. Other faults are creeping, meaning that the fault is actually moving over time. And so the ones that are locked are accumulating stress, and the ones that are creeping are less. So it's really important to determine which faults are locked and which are creeping. In this case, we're talking about a locked fault. Since the Earth is elastic, you'll have this, and this is moving, I think this one is right lateral motion. Then over time, since the crust is elastic, you'll have this bending here, which looks like a bending. It's an arctangent type function that as you move away from the fault, you have this arctangent movement. Remember, it's locked at the fault. And then when you have an earthquake, the fault ruptures, releasing the energy. And now instead of here, then the fault, then you have this co-seismic displacement. And using that kinds of information of the buildup of stress and the buildup of strain in the earth, you can then infer how the faults are moving within the earth. Right? So if you look at the right here, you have a strike slip environment, you have marks on the ground, and you want to know how it's moving within the crust. And so using this, we can do an inversion of the data, and that will give you then the motion of the faults, how deep the faults are, etc., and the different properties, the physical properties of the crust. So it's a really not a very non-unique problem. You have to really make a lot of assumptions in order to get a model of how the fault is slipping at depth. Okay. If you look at what we call transects across the San Andreas Fault, and remember before I showed you on the slide, you had this arctangent function as you go across the fault. So these transects go across the fault in different locations along the San Andreas Fault. And these over here, the profile H and G, they're basically, this one is locked, right? Because you have this arctangent type function. So we know that the fault is locked in this area. But if we look down here in the south, then you see that this motion is not arctangent, but you have this kind of drop off. And that's an area where the fault is creeping. So looking at these different profiles, we can get an idea of what's locked, what's creeping. And from that, we can then infer, earthquake recurrence rates, when the stress, when the strain has built up sufficiently, that will give you a high probability of an earthquake, and that kind of information, which then we translate it into hazard assessments. Now, this is a more complex picture. This is a map of Southern California and Northern Baja California, and this was the scene of the 2010 El Mayor Cucupa 7.2 earthquake, and this was a result of several faults that you see listed here. And these squares are GPS, GNSS stations. Oops, excuse me. Using this information from the surface, motions plus INSAR imagery, a lot of INSAR imagery, they're able to take this information, these observations on the surface, and we do what's called an inversion in order to then determine what's happening within the crust. So this is a fairly complex model of what's happening. This is a co-seismic model, which tells you what happened during the earthquake itself, while it ruptured. And this model is a post-seismic model, which then shows you how the slip is distributed and moves in the period after the earthquake stops shaking. And over time, you have this migration of slip at depth. You see here, we're down from about 0 to 15 kilometers depth. Here are the different slip rates. So it's broken up into different segments. And the fault inversion then allows you to determine the sense of slip and the amount of slip, that's how much it moves during the earthquake itself and in the post-seismic period. Right. And then there are also models for how the crust is moving linearly over time. So there's the co-seismic, which is at the rupture, there's the post-seismic, and then there's the interseismic period where the crust is accumulating a strain until the next event. Now, I'm going to talk a little bit about the higher rate GNSS measurements. And first, I'll just briefly go through the seismology and what that brings to the table. So we have this is the seismic network in the Western US. Of course, the seismology provides you the aftershocks, which delineate the geologic faults at depth. So that gives us an idea of where the faults are. And that information will then go into these fault inversion models. You also have this, you've had some presentations on paleoseismology, where you dig trenches across the fault in order to determine when the earthquakes occurred in the past. That gives you an idea of slip rate, and those are compared to GNSS derived slip rates. So we're comparing kind of geological rates to the let's say the current rates, which is always a challenge to then compare. Why don't they agree? And of course, the seismology is used for earthquake early warning, which is, they have a system now in the Western US. And there are over 1,000 of these sensors. So, so we have on one side we have the GNSS, geodesy, on the other side we have seismology. These are the typical seismic waves. These are the P wave first arrivals, S waves, these are body waves, and then followed by surface waves. The P waves are hardly felt. The S waves are what causes the shaking. Those are followed by more shaking by these other waves. So that's a background for the seismic waves. So what we've done is we've developed this methodology, we call it Seismogeodesy, where we take accelerometers, precise accelerometers, and we combine them with GNSS measurements. Now these are done, the GNSS measurements are now once per second, or it could be up to 10 times per second. Remember, the daily solutions are an average of all the information over a day. This is just displacement every second. So combining these two instruments, then we're able to then get a much higher rate of motion. You have certain advantages by in doing this combination. This is, we get two pieces of information. We get what's called broadband displacements. which are basically the displacements on the ground at a very high rate. You see the shaking plus the permanent motion, the co-seismic motion that you see over when the shaking stops. So with a typical with a seismic instrument, the broadband velocity instrument, you don't get the permanent displacement. So that's what the main advantage of having GNSS is, having this permanent displacement, this co-seismic displacement. The other advantages is that for a broadband seismometer, which is a very precise instrument, when you get very close to an earthquake, then it'll clip, I mean, it'll go off scale. So you can't get this full record if your broadband seismometer is very close to the earthquake. And that's, of course, where you want to be when we're talking about hazards. So that's one advantage of the GNSS seismic integration. And that the measurement of the permanent displacement is really important for rapid magnitude estimation, which is for things of early warning, like tsunami early warning and things like that. But what's more important is the instrument, the seismic instruments, because of their nature, they'll exhibit what's called magnitude saturation. What that means is that for large earthquakes, using just a seismic instrument, you will underestimate the magnitude once you get up to the higher magnitudes. I mean, that anything under over a magnitude 7.8 and above, you won't be able to distinguish that from a magnitude 9, which is of course very important to know. And with the GPS, the GNSS, you can then it doesn't experience this magnitude saturation. There's a lot of benefits from combining the two types of instruments, and we've done quite a bit of research in that area. In this, what am I doing with time? Let's see. Oh, it's getting late. All right, so this one, we want to distinguish the co-seismic. Remember, there's a co-seismic and a post-seismic period. So using this relationship of total energy, we're able to then determine not exactly, with a very good estimate of this is when the earthquake happens and when it stops the shaking. And that's what we call the co-seismic period. And that will vary could be from a minute to several minutes for the large earthquake. So what we're looking for is the transition from this co-seismic phase, where you have this permanent displacement, and the later post-seismic. Now, knowing the difference between the two is important in creating these fault models, and it has implications for the rheology of the crust. So it's important to know the transition from the co-seismic deformation to the post-seismic. And you see here an example from the Crest earthquake. And here you see what we did was we compared two different scenarios. One where you looked at the daily displacements, that is the typical 24-hour displacements, which usually what people use for these co-seismic models. So they have observations on the surface, and you invert them, as I mentioned before, in order to get the motion within the crust, the fault model, right? So this on the left is a model just using the 2 minutes of data. And the one on the right is using the whole day of data. So if you take the whole day of data, then you're mixing together the co-seismic and the post-seismic. And so this is the difference between the two. So you see that there is some, if you use the daily, you're actually mixing up the co-seismic and the post-seismic. So your models are a little bit skewed in terms of what you want to, what the motions within the crust. And so here you see that the difference was between the two. You'll have the migration of the slip over to the, in this case, to the north, west. And in this case, the period, 33 hours after the earthquake, is equivalent to a magnitude 6.2, or about 6.5% of the co-seismic moment. It's the amount of energy that's released during the earthquake. On the other hand, if you look at another earthquake, the Parkfield earthquake in 2004, I'll show you a movie, and this movie shows you the progression. See, this is the surface, how the stations are moving with time. And this is the time here, and this shows the misfit between the observations and the model. And here you see the deformation at depth at these different time intervals. And in this particular case, so this is, you can compare this to the models I showed before, which are based on 24 hours of data. Now this will give you a look in the crust at a very high temporal resolution. Right? And then these are the observations, and this is the inversion. That means taking the surface measurements and then inferring what's happening within the crust. Again, you have about from 0 to about 15 kilometers. And in this particular case, the co-seismic slip model has this moment, which is expressed in Newton meters, but this one is equivalent. The post-seismic model, the post-seismic model at 34 minutes, 24 hours, and 15.4 days have a cumulative post-seismic moment of 7%, 34%, and 100%. That means after 15.4 days, the moment release, or the amount of energy that's released, is 100% of what it's released during the earthquake itself. So in order to know how much strain is released during an earthquake, you have to be able to take into account the motion that occurs after the earthquake, as you go from the co-seismic period into the post-seismic period. So I think I'm going to stop here because I'm running out of time. I was going to talk about tsunami warning, but I'll leave that to another time. I think I have a concluding. Let me just go through. You'll see. There's my concluding slide. So thank you. This is a picture of the pier at Scripps Institution of Oceanography. So thank you for your attention. I'll take any questions.
Yehuda, thank you, and thank you again for making us very jealous of where you are right now and the view you have. At this point, if anyone has any questions they would like to ask, please do ask them directly, or if you for any reason you don't want to talk and it's easier for you to write in the chat, I can read that as well. But if anyone would like to have anything clarified or get further information on anything covered, then now is your chance. Yehuda, you were mentioning quite a bit about moving from, oh, sorry, we've got Gerald. Would you like to ask a question?
Yeah, hello. Yeah, enjoy that very much. In your slip models, I noticed that the cells get bigger with depth. And so at, when sort of 20, 25 kilometers, the cells are, well, a number of kilometers across. How do you decide how big the cells are? What governs that? I mean, it's very hard, of course.
That's why I said it's a very non-unique problem, and it's really not. It's not an invertible problem unless you start making some assumptions like the size of the cells. So you have to break up the ground into different cell sizes. You also have to make other assumptions. So it's really a matter of physical intuition. knowing where the aftershocks are. Aftershocks will tell you what the depth, the depth of when where the fault, the slipping occurs typically. So it's really it's kind of an art in order to determine how to break, how to model the underlying the crust. It's a lot of intuition and experience.
Yeah, great. Okay, thank you.
If you look at a single earthquake and you look at different papers, each one will have a different model. But the bottom line is you have to fit the surface observations. So as you play with the model, you want to see how well it fits what you measured on the surface. And then what you measured on the surface, you have to make sure that what you're measuring on the surface is really motion that's due to tectonic motion. As I mentioned, it could be complicated by other types of motion, which will then will bias your model. So it's kind of an art, somewhat of an art, but it's you have a physical intuition that comes into play. You also have to decide on different layers. There's different layer models where you have an elastic layer over a viscous elastic layer, and you can get a lot of models that will fit your data. So it's
thank you very much. Great
question.
Thank you.
Thank you. We have a question from Aphanisos Ganas in the chat. He says, do you see any value with current technology in detecting pre-seismic deformation?
Okay. Well, it depends what you call pre-seismic deformation. So there are papers now that show that there are variations in the interseismic rate when you approach an earthquake. And this is primarily with thrust earthquakes in Japan, South America, and there are some signals in the months before an earthquake. So there is, if you combine that with your longer term slip rates that kind of tell you how much the earth is accumulating strain, and then you see some anomalous signals beforehand, that'll give you an indication of, we think, of pre-seismic motions that give you some additional information on when an earthquake is more likely to happen. But it's still very, there aren't many cases of that. There isn't really anything any pre-seismic signals that will be right, that we see right before an earthquake happens. So that's kind of the holy grail of all this, is whether you can predict the earthquakes, and we're not even anywhere close to doing that. There are, so that's one of the reasons we're looking for these transient motions that I mentioned. And so the idea is, if you can find transient motions, if you can detect them, and some of them are very small, then you'd have a better idea of when an earthquake's going to occur.
Thank you.
That's pretty vague, right?
It's honest. It's honest, isn't it? It's where we are. We have a final question, which is, can we estimate the long-term slip rate in millimeters per year by having GNS data over 50 to 60 years?
Yeah, definitely. Right now we have 30 years of data, which is pretty good. Now, a lot of, again, these 50 years or 30 years are punctuated by earthquakes, depending where you are. In the most interesting areas, you're going to have earthquakes. So yeah, you can, that's also a challenge, is to distinguish then from interseismic from the transient, like the post-seismic deformation. So yeah, we have 30 years of time series, and we're continuing to measure. As I try to make the point that it's somewhat complicated because there really isn't an area that's of interest, of tectonic interest, that hasn't had some kind of earthquake over that period of time. So we can get long-term rate, but we also have to take into account these other, these transient motions, that not only tectonic motions, but the other types of motions that I mentioned, as well as artifacts in time series.
Great.
Thank you so much. Sorry, can I ask a question? Thank you so much. I'm working on a South Iceland seismic zone, and during these 60 years, almost like more than 20 earthquakes happened. And it's a really interesting area for calculating the long-term slip rate by GNSS data, because we have GPS data from 1987 or almost that time. And I was wondering if there is any good reference, because I searched a lot and I could not find really a good reference to see how I can progress in this field. I mean, how can I just reach from GNSS data to the sleep rate, specifically long-term sleep rate for hazard estimate? Yeah.
Where are you working?
In the South Iceland, in the Southwest Iceland, on the South Iceland seismic zone. It's like a transform fault zone, like a San Andreas Fault, but instead of like a simple left lateral transform zone, there is a bookshelf fault system of strike slip faults. And it's really interesting because in respect to the Pre-SHA, I'm really interested to calculate the long-term slip rate of this fault that is not really obvious on the ground. And
well, there's also the INSAR observations. Have you looked at that at all? There's some good data from over Iceland.
Yes.
Yeah, it's complicated there because you also have, volcanism, quite a few earthquakes. Yeah, it's a challenge. It's a challenge. I should mention, indeed, there are areas of 50 years of measurements, because these survey mode measurements began in about the mid-1980s. So there are areas that do have 50 years of measurements. But it's difficult to determine what the long-term rate. So essentially what you have to start with are the plate motions, right? So the plate motions provide you with a rate based on just the plates moving with respect to each other. So that's your starting point, and then you have to fill in. When you go more and more local, then you have to fill in that information from. It could be also from geological observations. The geological observations are the best source of the long-term slip rates, what we call geological slip rates. And then you also have these paleo seismic, where they trench across these different faults. And more complicated if your faults are under the ocean.
Yeah. Thank you so much.
We have one more final question. I already said final question, but one more final question from the chat, which was saying that inversion for slip model is a routine work now. This is from Alex, but he says, how can we translate slip model into practical evaluation of earthquake hazards? Could you please give me your insights on this? That's quite a big question to finish on, but perhaps.
Yeah, well, so in the beginning, I showed these maps of probabilities. And so using all the information, like the slip rates, the geological information, the seismic information, then you can translate the hazard into risk. That gives you the input by combining all these different types of observations. You can then take the slip rates and then create probability maps, and how you would expect the ground to shake, or ground motion models, and how you expect it to shake based on the the energy that's released, because the slip rates basically tell you how much energy is going to be released at the earthquake. And from that, you can then determine your, the moment release, and then how the ground motion is going to occur, and how that will impact, structural integrity and things like that. That answers the question, hopefully.
Thank you. And we will be learning more about some of those steps later in the learning series. So there's a little sort of forward for you. I just want to say thank you again, particularly to Yehuda. I appreciate it. I think it was 9 a.m. on a Monday morning for you when you gave this talk. So thank you very much. And just to flag to everyone that our next talk will be on Monday, the 12th of July at 4 o'clock Central European summertime. So 4 o'clock on mainland Europe and 3 p.m. in the UK. Everyone else, I'm afraid you're going to have to work out the time for yourselves. And that's going to be given by John Douglas. And it's on estimating earthquake ground motions, background, methods, and challenges. So we'll be learning more about ground motion equations from John Douglas next time, slightly earlier in the day. Yehuda, thank you again for your time, and thank you everyone who joined us today.
Yeah, thank you, and it was a pleasure to meet with you and spend some time together.
Thank you again. Really appreciate it. Goodbye.
Bye.